This method is called reduction of order. It's useful for finding the second homogeneous solution. If you're only given one, you have to be given one homogeneous solution to a second order linear homogeneous differential equation. All right, so this equation here, it's constant coefficient. We can actually solve it really easily. And you could just write down y2 here. It ends up being x e to the 4x. But as an example, we're going to apply reduction of order to this differential equation we already know how to solve. So the idea is not that bad. So it's going to be, we're going to do a guess, like a lot of the methods. So we're going to say the second homogeneous solution, y2, is equal to some unknown function v of x times y1, the homogeneous solution that we do know. And then for us, so I'm just going to write v as v, and then e to the 4x as y1. Then we're going to take some derivatives, plug them into the differential equation, and try and solve for this unknown function v. And this cool thing happens where the new differential equation you get for v is actually simpler. So let's get started here. So I'm going to need y2 prime, so I've got to compute that. So this is a product rule, so this will be v prime e to the 4x. That's the first half of the product rule, plus the non-derivative of the v times the derivative e to the 4x times 4 e to the 4x. I usually like to simplify this as I go. It's a little nicer usually. So both those terms have e to the 4x in them, so this is v prime plus 4v times e to the 4x. All right, next up we need to compute y2 double prime. All right, well that's going to be derivative of the first term here for the product rule. That's v double prime plus 4v prime times e to the 4x plus the non-derivative of the first terms, that's v prime plus 4v, and then times the derivative of the second term, that's 4e to the 4x again. Then I want to simplify this if I can, so I've got a v double prime, I have a 4v prime here and another 4v prime here, so that's 8v prime. Then I've got, let's see, 4 times 4v plus 16v. v, and that's all times e to the 4x. All right, now we get to plug it all into the original differential equation. So we're going to have y2 double prime minus 8y2 prime plus 16y2. That's all supposed to equal 0. So substituting in y2 double prime for this, we get, let's see, v double prime plus 8v prime plus 16v times e to the 4x. Then I've got a minus 8 times y2 prime, here it is, v prime plus 4v times e to the 4x. And then I've got a plus 16 times y2, which is just v e to the 4x. And that's all supposed to equal 0. Alright, so all of these terms is an e to the 4x in it, so I'm going to write kind of a big parenthesis, and I'm going to combine everything together. So the only v double prime term I have is here, so I just have v double prime. And then I have a plus 8v prime. But I also have a minus 8 times v prime, so minus 8v prime. And then I have a plus 16v, so plus 16v. Then I have a minus 8 times 4v, so minus 32v. Then I've got another plus 16v. And that's all times e to the 4x. And that all still needs to equal 0. Right, if you look at this, right, I have v double prime, so there's one of those. Then I have 8v prime minus 8v prime, so that's 0v prime. Then I have 16v minus 32v plus 16v. Well, that's 32 minus 32, so I have 0v. All times e to the 4x equals 0. So the new differential equation I have to solve, which is hardly a differential equation anymore, is v double prime times e to the 4x equals 0. And then the next thing is e to the 4x, no matter what x is, can never be 0. So that means that we actually have v double prime has to equal 0. Alright, so we went from a much harder differential equation, y double prime minus 8y prime plus 16y equals 0, to this much simpler to solve differential equation, b double prime equals 0. And this one is quite straightforward. We can just integrate it. So if we integrate b double prime dx equals integral of 0 dx, well, the integral of v double prime, that's b prime, that's going to equal some constant. I'll call it a capital C. And then we integrate again. So we integrate b prime dx equals the integral of some constant dx. Well, integral v prime, that's v, put the of x back on. And then integral of a constant is a constant times x plus another constant of integration I'll call d. So then if I want to look back and figure out what the second homogeneous solution was, well, y2 we said was just b of x times y1, and then here we're getting, cx plus d times e to the 4x. So then we get cx e to the 4x plus d e to the 4x. Now if we went through and kind of just blindly put that in for the homogeneous solutions, right, y homogeneous is equal to a constant c1 y1 plus c2 y2. That would give us, I need the space. So c1 e to the 4x plus c2 times cx e to the 4x plus d e to the 4x. So first, that's a lot of constants. So we have this capital C, capital D here. We have C1 and C2. We also essentially duplicate the first homogeneous solution right now in the second homogeneous solution. So right, if I take C2 times D times e to the 4x, well, that's a constant times e to the 4x. That's already here. We have a constant times e to the 4x. So we really don't need another e to the 4x inside the second homogeneous solution. And then we also have, C2 times C times x e to the 4x. That one is unique though. So right, x e to the 4x is a new homogeneous solution. So what we're going to do actually is we're going to choose y2 is equal to just x e to the 4x. And that's because x e to the 4x is fundamentally different from the first homogeneous solution, the one we already knew, which was just e to the 4x by itself. And then we can do that. We don't have all these extra constants, and we can still say that y homogeneous is c1 y1 plus c2 y2, which is going to be c1 e to the 4x plus c2 x e to the 4x. And now we get the second solution to the repeated root case that we already knew about. And right, so keep that in mind when you're solving here. In general, it's a good idea, right, to have the constants of integration coming in. You just want to make sure that you get the new unique function popping out for the second homogeneous term you're solving for, but you in general can trim out some constants, and usually there'll be the homogeneous solution you already know kind of repeated in there, and you just want to extract out the brand new term for your second homogeneous solution.